All right. I want to start by thanking the organizers for putting together this fantastic workshop. I've learned a ton already, and I'm very excited to be able. I'm very excited to tell you about some recent work that I've been doing with some fantastic collaborators. And depending on timing, I might get to talking about things that haven't appeared yet, also with the linear combination of these folks. So let me just dive in. The talk is basically about theta terms and their consequences. And let me just make sure we use the same language. So many quantum field theories in d space-time dimensions have 2π periodic theta terms. Okay, and as I think we all know, these theta terms typically appear as coefficients of what are called topological terms in an action. So you'll have some expression like that in the action, and then q of x is some total derivative such that when you integrate it, you get an integer. Okay, that's the typical situation. And the coefficient of this kind of term is called the theta term, and it's typically 2π periodic. What I'm going to do in this talk, at least initially, is to discuss a different way for quantum field theories to have periodic couplings. And I'll focus on something that we decided to call the Cheshire theta term. You probably don't know what that is because we just made up a name, but hopefully you'll see what I mean by that in a second. I realize this is an audience with a fair number of condensed matter folks, so I apologize for this, but I'll illustrate why you might care about this kind of term by an application to particle phenomenology. But I'll leave it as an exercise to the audience to find the condensed matter application. I am actually pretty sure there should be some. And then, depending on timing, because if I'm running out of time, I'll be very happy to just stop with this. But if there's time, I'd like to explain some relations between this stuff and the Witten effect in electromagnetism. And along the way, I'd like to try to convince you that there's actually more to the Witten effect than is usually discussed. And finally, and this is the least likely thing for me to actually get to, if I have time, I'll tell you about generalizations of the Witten effect. Okay, so let me just dive in. The first thing that I should do, given that this is an international conference, is explain the name. Okay, so Alice in Wonderland is a somewhat famous, at least in Britain and the UK, children's book from the 19th century. And in that book, there's a child named Alice who, for some obscure set of reasons, falls into a rabbit hole and ends up in a magical land full of creatures that are themselves quite magical and often very creepy. Okay, so this was the Disney version where the creatures look very friendly, but in the book, if you read it, they're kind of terrifying. And one of the creepy creatures, perhaps the single most famous one, is the Cheshire cat. Okay, and so the key feature of the Cheshire cat is that it likes to turn invisible, but not completely. Quite often, it chooses to disappear in such a way that actually all you see is its grin. And if you see that at night, somewhere in the forest, just this thing, it's pretty creepy, right? So the Cheshire theta term is also almost invisible, except for its grin. I'll try to convince you of that momentarily. Okay, so let me explain to you the setup in which these kinds of two-part periodic couplings can appear. So let's consider quantum field theory in d space-time dimensions, Euclidean space-time dimensions. And let's say that this quantum field theory includes some compact scalar field, 2π periodic scalar field, with a U1 d-2 form symmetry acting on it. I'll denote it like that. And that type of symmetry just counts vortices. Okay? And then I'll also assume that the field theory also includes some other fields, let's say psi, that are acted on by some zero form symmetry, some conventional symmetry, which doesn't have any 't Hooft anomalies. Okay? What I want to emphasize is that this symmetry that acts on these fields is not the shift symmetry of the scalar. Okay? The shift symmetry of the scalar will come in later, but for the moment, I'm not even going to assume there is such a symmetry. Right, so I have these two symmetries, this d-2 form symmetry that counts vortices and some other U10 form symmetry that, roughly speaking, counts particles created by this other field. And now we can think about the path integral. So here's a schematic representation of a path integral for this kind of model. And in writing this path integral, I have chosen to turn on a background field for this symmetry, a background gauge field, which I'm calling A. Okay? And the assumption that there's no 't Hooft anomaly for the symmetry means that I can do this, and the partition function or the path integral will be invariant under background gauge transformations for A. Okay? So that looks like this, okay? Hopefully everybody can see the thing at the bottom. So you shift A by d chi, sorry, where chi is a 2 pi periodic scalar itself, and that leaves the path integral invariant. Okay, so this is the class of models that the beginning of my talk will apply to. Okay? Okay, so the Cheshire theta parameter will appear if you do the following weird thing. You can try to replace this background gauge field A by theta hat over 2 pi d phi. Phi is my physical compact scalar, and theta hat is about to be my 2 pi periodic parameter. I'm calling it theta hat to distinguish it from standard theta terms. You'll see that this is really, in general, quite different looking from a standard theta term. Now, one thing I want to note is that the path integral sums over phi by definition. So in doing this, we've gauged U10 a little bit, only a little bit. So we gauged it because, since we're summing over this, we're basically summing over these. But we're not doing a completely free sum. For one thing, dA is necessarily 0, right? A is flat. And also, this would-be gauge field is completely tied to this other field, up to gauge transformations. Okay? But one interesting thing that you can deduce just from this rather formal construction is that the physics has got to be 2 pi periodic in theta hat. So how do we see that? Well, we take this thing, we shift theta hat by 2 pi, and we see that A shifts by d phi, and that's a properly quantized gauge transformation. And we have assumed that our path integral is invariant under gauge transformations. Therefore, the path integral doesn't change when you do this, and therefore the physics only depends on this funny parameter, theta hat, modulo 2 pi. If it depends on it at all. I'm about to show you that it does depend on it, but only modulo 2 pi. So let's try to make that more concrete. Okay, this is a bit formal, so let's make it concrete. For example, let's say the other field that we have in the model, in addition to the compact boson, is a Dirac fermion. Okay, and let's say that we're working in, well, really any dimension, but then it's going to have some symmetry that rotates it. Okay, I'm going to call it the U1 vector symmetry. And that's what my zero form symmetry is going to be. And then the Cheshire theta term looks like that. Okay. So what I want to emphasize is that this is, whatever this is, okay, it's definitely not a standard theta term. Why? Well, one way to see it is if D is 4, so if we're in 4 space-time dimensions in our world, and you take the standard canonical normalization for the scalar field phi, where it would have mass dimension 1, and then stare at this. This thing has dimension 3. The derivative gives you an extra 1, and so this is a dimension 5 operator. Okay, and what I'm telling you is that its coefficient, suitably normalized, is 2 pi periodic. That is not how standard theta terms appear. Standard theta terms are built out of classically marginal things. This ain't that. Okay? Now, naively, you shouldn't write this. And historically, people did not, as far as I know. Because this term vanishes after integrating by parts and using the equations of motion. Because if you integrate by parts, you move the derivative onto this thing. I'm assuming that the vector symmetry of the fermion is conserved. There's a conserved current, right? So then you'll get 0. And if you consult review articles by famous people or textbooks about effective field theory, they typically have statements like, you're supposed to build effective field theory by writing all terms allowed by symmetries, and then throw out anything which is zero by equations of motion at lower order or integration by parts or both. Okay. And the reason people say that is that anything that can be set to zero that way cannot possibly contribute to particle-particle scattering. And if that's all you ever want to study, then that's correct. Okay. And indeed, this parameter, the reason it's kind of like the Cheshire cat, it's almost invisible, is because it doesn't contribute to particle-particle scattering. But it's not quite invisible. It has a grin. It does act on other stuff. Okay, so let me explain how that works. The key point, okay, is that this funny gauge field that's built out of the compact boson is designed in such a way that it has non-trivial holonomies around vortices. So if you integrate this quantity on a circle that goes around some vortices, then you'll get theta hat over 2 pi times, just theta hat times n, where n is the number of vortices inside the contour. That's how this thing is built. So what does that mean? Well, it means that if you have a particle that carries some charge under this U1 zero form symmetry, okay, let's say charge Q, and it goes around a vortex built out of the compact boson, then that particle will pick up an Aharonov-Bohm phase like that. Okay? So the particles created by psi in the presence of this term, in my previous example, will see an effective gauge field just like the gauge field outside of a solenoid in E and M. But I want to emphasize here, at no point are there propagating gauge fields. Okay, right? There's no photons. Before I continue, any questions? Feel free to interrupt. Yes, go ahead.
Working, but I don't know, maybe not. Is it exactly like gauging with a flat connection? Or?
It's similar to gauging with a flat connection, but it isn't. Because generally, if you gauge with a flat connection, you sum over all flat connections. And we're explicitly not doing that. Okay. We're summing over flat connections that are built out of some different physical field. So it's kind of a restricted version of flat gauging, which is itself a restricted version of gauging.
Okay, no, I understand that, but imagine that, I mean, in any case, your phi was disconnected from...
yes, yes.
So in some sense, I could say I introduce phi to gauge. So if I would do that, that would be flat gauging or not?
I still don't think that this is if you were to erase all of the dynamics of independent dynamics of phi, okay, and just write this and then sum over all possible phis, this would be flat gauging. Okay. But the thing is, phi has its own dynamics.
Okay.
And unlike in this, like the simplest example that I showed you with just a direct fermion that only couples using this term, the compact boson and the fermion could have all kinds of couplings to each other as long as they preserve the symmetries I've assumed. This all works. Yeah. But thanks for the question. Yeah, we wondered about that initially as well. Okay. So basically what this thing does for a living is to produce Aharonov-Bohm effects. That's what this theta term does. Okay. Now, another thing that I want to say about it before getting to the who cares question is that the Aharonov-Bohm effect that is induced by this Cheshire theta coupling is actually quite robust. For example, the only thing I've said about the shift symmetry for phi is that I don't care about it. Okay, so it could be there, but I haven't assumed it. I didn't need it. So everything I've said goes through if it's not there. You could try to kill this term by trying to impose some discrete symmetries. For example, you could try to say that maybe there's some symmetry that flips the sign of phi, the compact scalar. And well, that will constrain this term, but it won't actually kill it, because the 2 pi periodicity would then mean that there are two allowed values, theta hat equals 0 and theta hat equals pi, just like with the theta term in Yang-Mills theory, or for that matter, the theta term in Maxwell theory. You could wonder what happens if you break the zero form symmetry down to a discrete subgroup. That still doesn't kill this. Because if that happens, then if we go back to how I motivated all of this, to try to set this up, I would need to turn on, instead of a U1 background field, which is what I did initially for this thing, now this background gauge field that I use, it should be a ZK background gauge field. ZK background gauge fields can be thought of as something that satisfies this kind of relation. Okay, so K times the gauge field is equal to D of some 2 pi periodic thing. And if you compare to this Cheshire theta thing, where this is what we write, okay, it will be you'll get a proper ZK gauge field provided that this Cheshire theta parameter is itself quantized appropriately. So it could be 0, 2 pi over k, 4 pi over k, and so on. So it is true that you could completely obliterate this by breaking this to nothing. But if you don't break it to nothing, then there will be something left. And well, soon, but not immediately, I'll explain that this Cheshire theta parameter has another effect in addition to the Aharonov-Bohm effect. It induces some interesting Witten effect. But that's not immediately important, so don't worry about it. I feel like this has been a bit too formal. Yeah, I see a question.
Does anything happen if I break the U1 D minus 2 form symmetry?
Good. The U1 D minus 2 form symmetry is a little hard to break, but if it's really obliterated, then you're not really going to have vortices. And then there's nothing to discuss because there's no Aharonov-Bohm effect. So yeah, if you really kill the if you break the U1 D minus 2 form symmetry somehow to discrete symmetry, that's not trivial, then something survives. But if you break it completely, then it's gone.
Okay, thanks.
Yeah, thanks. Right. So I feel like I've been telling you a bunch of formal stuff, although not as formal as I'll torture you with later. So what I'm going to do is try to address the who cares question by telling you about a possible application. So as a change of tack. Okay, so the standard model, the SM, explicitly violates the parity P and charge contradiction times parity CP symmetries. And the QCD action, which is a part of the standard model, has a classically marginal P and CP violating 2 pi theta parameter that I think everybody here has heard of since before, well, many people before I was born. It looks like that. And well, this causes a sort of conceptual problem because there's no effective field theory reason why this parameter should be 0. And generic short distance completions of the standard model, in fact, give you order 1 values for this parameter theta of Yang-Mills or QCD. And well, if theta is order 1, then it turns out you can show that this induces, for example, a non-zero electric dipole moment for the neutron. Now, the value for this electric dipole moment is really very small. That would be induced by order 1 theta. So small enough that we wouldn't care in everyday life at all. But experiments actually show that this is not what you get. I mean, actually, the true value of the electric dipole moment is like 10 to the minus 10 times smaller. So for some reason, theta is real close to 0, and there's no obvious effective field theory reason why this would be if you just assume the standard model, basically. So what I just described, it constitutes one of the big open problems in particle physics, and it's called the strong CP problem. Okay. There are many approaches to the strong CP problem. Perhaps the most popular way is to couple the standard model to a 2 pi periodic scalar field phi called the axion. That goes back to, well, at least Peche and Quinn around the late 70s. So here's what the coupling looks like. Basically, you promote theta to a dynamical field. So phi, the axion, now has its own kinetic term with some dimensionful parameter here, which is usually called the axion decay constant. Think of it as like if phi comes from spontaneous symmetry breaking of something, then FPQ is like the VEV of whatever condensed to give you the Goldstone boson, which is phi, pseudonumber Goldstone boson. So if you do this, if you modify the standard model in this way by adding this extra particle, then the QCD theta term can just be absorbed by shifting the axion. And then the actual practical value of theta that actually matters gets replaced by the value of the axion at the minimum of whatever potential is induced for it by, for example, QCD effects. And if QCD is the only source of breaking of the shift symmetry for the axion to a good enough approximation, that one sentence is like 1,000 papers on FPH, making sure that works. But it can be done. And then the minimum of the axion potential really will be basically at 0, and you'll solve the strong CP problem by postulating roughly one extra particle. So that sounds nice. So the point of the axion is to get rid of a 2-pi periodic coupling. But it also gives you another one, which, as far as I know, wasn't particularly discussed, and it's this one. Okay, so this is just the Cheshire theta parameter that I talked about before. And here, J mu B minus L is the conserved current for the B minus L symmetry, the only U1 symmetry of the standard model. That isn't anomalous. Now, C or P symmetries, if they were actually symmetries of the standard model, would force theta hat to be 0 or pi. But actually, they're not symmetries of the standard model. They're maximally violated. So any value of theta hat is allowed from the point of view of effective field theory. It could be anything. So I think the effective field theory philosophy would then be to say that the value of the axion decay constant and theta hat should be viewed as free parameters and should be constrained by data. I should note there is also an anomaly-free Z3 symmetry in the standard model, which is B plus L. And so there's a discrete theta parameter you could also add, but don't worry about it. Questions so far? Okay. So these funny generalized theta terms, as I said before, their role in life is to give you Aharonov-Bohm effects. So here, they give you an Aharonov-Bohm phase for leptons or quarks as they move around axion strings. And I want to emphasize that this Aharonov-Bohm phase happens to be present even if there's no axion shift symmetry, in which case axion strings are actually attached to domain walls. But that's fine. Okay, you still get the Aharonov-Bohm effect. Now, rather famously in the literature on the Aharonov-Bohm effect, going back to Aharonov and Bohm themselves, whenever you have an Aharonov-Bohm effect, you have scattering. There's a non-trivial scattering amplitude for particles to scatter on a vortex. Now, typically, you get Aharonov-Bohm effects for vortices that carry magnetic flux, right? Those are called local vortex strings or ANO vortices, Abrikosov-Nielsen-Olesen vortices. And in that situation, the differential scattering cross-section takes the following form. So there's something that depends on the flux carried by the vortex in units of the flux quantum, the gauge charge of whatever particle that is trying to scatter on the string, and then the momentum and scattering angle in the transverse plane to the string. Okay, so this formula has been extensively discussed and rederived in many different ways, for the last 50, 60 years. And normally this is thought to be only a property of local strings. But what we're saying is that since the Cheshire theta term is allowed, and in effective field theory, everything that is allowed is mandatory, then the same effect and the same scattering should show up for global axion strings. And axion strings are very often discussed in cosmology. They're very hard to get a hand on in our everyday life, but they may well have been important in the evolution of the universe early on. Okay. Any questions? Yes.
But if axion is massive, then these strings cannot exist without a domain wall attached to it.
Yes,
so,
I had a slide about that.
Yeah.
That's right.
Yeah, okay.
That's right. So the extent to which you care about the domain walls that have to get attached to axion string loops depends on where you are in the cosmological history. So, that becomes really important after the QCD phase transition. Before that, it's not so important. But this effect is there regardless. Yeah. Thank you. So I'm not a phenomenologist by training, so please be gentle with your questions about this part. But this is what I think is going on. Okay, one of my collaborators is definitely a phenomenologist by training. So suppose that the PQ symmetry, the would-be shift symmetry of the axion, if it had a shift symmetry, that it breaks spontaneously after inflation ends. This doesn't have to be true, but it is true in many, many, many models. If that happens, then it's believed that the phase transition will produce a big network of cosmic strings. Okay? And then this happens in the early universe, and then the universe keeps expanding. And the axion strings move around and they wiggle, they reconnect in various interesting ways. People write many, many learned papers about doing simulations for that. The key point is that as they do all this, they emit axions and gravitational waves. Perhaps other things too, but those are the obvious ones. And if there's non-trivial scattering between axion strings or any kind of string and the plasma of particles in the early universe, there'll be some friction from the plasma of particles in the early universe against the axion strings. So it will affect their motion. It'll basically try to slow them down. And this has long been known and studied for like local cosmic strings, not axion strings. And it is known that taking this effect into account for axions or for local cosmic strings that carry some non-trivial flux, this affects their motion in the early universe and ends up leading to a suppression of gravitational wave emission for high frequencies. It turns out not to be so important for low-frequency gravitational wave emission, but it is very important for high-frequency gravitational wave emission for some, slightly complicated set of reasons. And so normally that's thought of as something that only affects like local cosmic strings, which appear in many models, of course. But what we're saying, okay, is if there's no clear reason for theta hat to be 0 or very, very small, and it's not obvious what reason that would be, from effective field theory at least, then it'll be order 1. And that would produce the same cutoff on the gravitational wave spectrum, the same suppression of the gravitational wave spectrum for high frequencies for axion string gravitational wave emission. Okay? So that means that if we're lucky, the value of theta hat, and through it, like really high scale physics, might be constrainable by future gravitational wave observation experiments. So, okay, so you have to do some estimates to see whether this is nuts or not. So we tried. So here's a rough plot that's in our paper. So we took a couple of different representative values for what the PQ scale might be. And we used the standard formulas for gravitational wave spectrum as a function of frequency. And okay, so the solid lines that you see here, okay, these are the curves that everybody would write. In fact, these are the curves that appear in the literature. They are going to be reliable for sufficiently low frequencies. Okay, so for this part. And then the friction effects that I told you about earlier will kick in at some frequency, okay, which depends on what FPQ actually is. And after that, you should get a significant suppression. Now, exactly what the suppression is requires a lot of detailed numerical analysis. We don't actually know. So normally they would continue just like that along the upper edge of the colored regions. Okay, but if there's this friction on the axion, if there's friction on the standard normal plasma, these curves have to get suppressed to be somewhere inside of these regions. So then the next question is there any chance at all this could be observable? Because we're talking about pretty high frequency gravitational waves here. Look at this, the lower axis. And fortunately, there's at least one proposed gravitational wave experiment that has certainly not been built yet by these authors, whose sensitivity is illustrated here, that has at least a chance of seeing this. Arguably, this is another motivation for thinking about other proposals for measuring really high-frequency gravitational waves. Okay, so there's a chance that these kind of Cheshire theta terms might be interesting from a like beyond the standard model physics perspective. Okay. How much time do I have left? How am I doing? 10 minutes. Okay, I'll get through part 2 and then jettison part 3. Okay, perfect. So let me get back to somewhat more formal things, namely the Witten effect, which I'll argue is very closely connected to what I talked about a short time ago. And it's going to be in a paper that's coming soon with Maria and Shi. So to start with, I want to make sure that everybody remembers what the Witten effect is. So the Witten effect is something that occurs, for example, in 4D U1 Maxwell gauge theory. That theory has a one-form, well, has two one-form symmetries, an electric U1 one-form symmetry and a magnetic U1 one-form symmetry. And well, they're U1 symmetries, so the charged objects have integer charges, E and M. Okay, so the charged objects are Wilson lines and 't Hooft lines. Well, everybody knows the Maxwell U1 gauge theory has a 2-pi periodic theta term, like that. M4 is the space-time manifold, which I'm assuming to be spin. So the standard Witten effect, due to, as you could guess, Witten, is that theta makes the physical electric charge fractional. So by physical electric charge, I mean the thing that is measured by the Gauss law in the presence of theta takes these values. And for generic values of theta, this is a fractional number. What it means is that magnetic monopoles, which have M of plus or minus 1 and E of 0, become dions. They become something that carries both magnetic charge, which is integer, and physically electric charge, which is fractional. Okay. Now, this may have seemed like I just veered into talking about some unconnected thing to what I've been talking about. So let's go back to the Cheshire theta term that I talked about earlier. Suppose that in addition to the symmetries that I really assumed initially, there really is a shift symmetry for phi. Okay? And if there is such a symmetry, you can't stop me from asking what happens if I turn in a background field for that shift symmetry. And well, then the theta term gets modified like that. Okay? So this J0 is a current for the zero form symmetry that counts some particles that have nothing to do with phi. And A is the background field for that shift symmetry. So if you stare at this long enough and recall how gauge fields couple to currents, you will see that particles with charge Q under the original zero form symmetry, U1, pick up a charge under the shift symmetry of phi, which is fractional. This is in complete analogy to the standard Witten effect. It is a Witten effect, just some generalized version of it for this particular situation. If you break the shift symmetry, then this Witten effect disappears because the associated charge doesn't make sense to ask about, right? But there is something that is left, which is the Aharonov-Bohm phases that I told you about before. So noticing this leads to a pretty obvious question. What happens to the Witten effect of Maxwell gauge theory if you somehow obliterate the electric one-form symmetry? That's the analog of obliterating this symmetry. Is there something left? Could there be some funny Aharonov-Bohm effect hiding in the Witten effect of E and M? So I want to try to argue that the answer is yes. Suppose that AM is a two-form background gauge field for the magnetic symmetry of Maxwell theory, and you stick Maxwell theory on a manifold that looks like that, for example. And then you can take one of the circles in the torus to be Euclidean time and turn on a holonomy for this field on the S2 that takes some value, let's say chi, the chi. And then if you do that, the partition function will get contributions from twisted sector operators, but twists are by this magnetic symmetry. And that just means it will get contributions from operators that are non-genuine lines. They're attached to topological surfaces. So if you compute the associated partition function, it will look like this. There'll be some fluctuation determinant out front. Don't worry about it. And then you'll have this kind of thing. E and M are the electric and magnetic charges under the U1 one-form symmetries. And then you can see here that, E contributes like that, okay? So this is like the effective electric charge due to theta. So it's kind of fractionalized due to theta. But then the twist also does some funny business. It also messes with the quantization of E. Instead of just being integers, it's integers with a shift, which is determined by the holonomy of the background gauge field. So, excuse me, that's a consequence of the 't Hooft anomaly between these two one-form symmetries. And so if you stare at this long enough, you'll see that it seems like twisting by the magnetic symmetry is closely related to turning on the theta term. So that's a hint for what's really going on, which is that you can show that the Hilbert space of operators with a fixed magnetic charge, okay, with a given twist and a given theta angle can be related to Hilbert space of operators with the same charge and a different twist, but with 0 theta angle. So that means that if you take theta that's greater than 0 and consider operators with charge M in the vacuum sector, so meaning no twist, okay, those act exactly the same way as operators in the theory with theta equals 0, but in the twist theta M sector. So the effect of theta, the effect of the Maxwell theta term is to reshuffle the twisted and vacuum sectors of Maxwell theory with a fixed magnetic charge. And in fact, the same comments apply to the Cheshire theta term. It actually shuffles the fixed charge twisted and vacuum sectors with respect to the two symmetries I assumed from the very beginning. Now, if in addition to the U1 magnetic symmetry, there's also a U1 electric symmetry, as there was in the previous slide, then the mixed 't Hooft anomaly will lead to charge fractionalization. And usually, charge fractionalization is used as a definition of the Witten effect. But this computation actually shows that the thing that is usually viewed as a definition of the Witten effect requires two things. One is this twisted sector shuffle that I talked about, which only depends on the magnetic one-form symmetry. And the other thing is that it requires an extra symmetry, the electric one-form symmetry, to also be there and have the right 't Hooft anomaly. So somehow this twisted sector shuffle is it requires fewer assumptions. So we think it's the right starting point for generalizations, and so we're choosing to call it the primary Witten effect. So the things that you might wonder, and what I'll basically end with, are what are the physical implications of this primary Witten effect, this twisted sector shuffle, and I won't get to generalizing it. So what we saw in the Cheshire theta term example is that the primary effect of this Cheshire theta term, if you don't have a shift symmetry, is just to give you an Aharonov-Bohm effect. That can actually be derived directly from the twisted sector shuffle. It's a slightly technical computation, so I'm not showing it to you already at the end of the talk pretty much, but it's not very hard to do. And in fact, this is how it works in general. The primary consequence, the physical consequence of this twisted sector shuffle induced by the theta term in Maxwell theory is an Aharonov-Bohm effect. So to get a feeling for how this works in electromagnetism, imagine inserting a magnetic monopole into the theory. So that would be shifting the gauge field to something that inserts a monopole plus some fluctuations over that. So in the theta term, it just shifts the theta term to these two things. And now stare at this term for a second. And remember that if we had turned on a background field for the magnetic symmetry, it would have coupled like that. You compare this to that, and you realize that inserting a monopole is like turning on an effective background field for the magnetic symmetry. But that background field has an interesting property. It's got a fixed holonomy, okay, which is fixed in terms of the theta angle. So this is very much parallel to how inserting a vortex into a field theory with a Cheshire theta hat term induces a non-trivial holonomy. Okay. And well, if you think about it, then the excitations created by 2 lines should experience an Aharonov-Bohm effect when they move around monopoles. But a subtlety with this is that the magnetic symmetry is spontaneously broken in pure Maxwell theory, and that makes that very hard to see. But that's easy enough to fix. You just add, let's say, unit charge Higgs scalar field, and you can push the resulting abelian Higgs model into the Higgs phase. And in the Higgs phase, the magnetic symmetry gets restored, and the electric symmetry is very helpfully obliterated. And so you might think that the standard theta term has no effect in the Higgs phase. In particular, the standard Witten effect is destroyed as well, because it's not meaningful to discuss electric charge fractionalization. However, the primary Witten effect only cares about this symmetry. So it's still there. And so theta can still affect the physics. In particular, hitting the vacuum within a 12th line operator creates a local vortex string with a finite tension that carries some magnetic flux. And then these vortex strings experience an Aharonov-Bohm effect when they move around the magnetic monopole. So here's a magnetic monopole. Of course, it's confined in the Higgs phase. So there's a string that goes off somewhere to an anti-monopole. But here's a vortex string, and you can move it like this, and like that, and like that. And along the way, it'll accumulate a phase. Now, in the process of doing this, there are all kinds of complicated string-string interactions. So the magnitude of the correlator is something that's very hard to control. It'll do some interesting stuff that you have to calculate carefully. But the universal part of this that you can do without computation is to see that there's an Aharonov-Bohm phase in this process. Okay. I think I'm running out of time. So probably shouldn't talk about this. It's much more formal anyway. It has to do with STS transformations, which would connect to Masaki Oshikawa's talk, but let me not, okay? The things that I want you to take away from this talk is that quantum field theories with compact scalars have peculiar 2-pi periodic couplings called Cheshire theta parameters, and they may have observable consequences in our universe. The other thing is that this is all related to some aspect of the Witten effect that is not usually discussed, at least anywhere we could find. And the thing I haven't told you, but that can all be massively generalized using STS transformations, getting connections to things like Kennedy-Saki transformations. So there's a big open problem that I want to highlight because I'm hoping that some of you can help solve it, which is that at the moment, we actually don't have a good idea for how to tell if this type of effect, exotic theta term is actually induced by some RG flow from something else. Feel free to ask me why that's confusing later. There has to be a way of figuring it out, but like we got confused about it. So in particular, we at the moment do not know which UV axion models, like KSTZ or whatever, like which of them, if any, produce a non-trivial value for theta hat. We also don't know whether, for example, there is a non-trivial Cheshire theta term in large NQCD. So large NQCD has massless theta prime boson, or nearly massless. And in the chiral Lagrangian, you could, in principle, add a term like this. But is it induced by the dynamics? I have no idea. And the last open question that, again, maybe some of you can help with, and perhaps it will be connected to the next talk by Yoshimasa, maybe, I'm not sure, you might wonder whether systems which have distinct values of these generalized theta terms that are quantized for whatever reason, whether they necessarily lie in distinct phases. Okay, so sometimes the answer is yes, but we only know this like example by example. And in many examples, we actually don't know the answer. So it'd be nice to get a general understanding. So with that, I think I'm out of time, so I should shut up. Thank you.
Okay. Right. So thank you very much for the great talk. Very cool. My question is on the strong CP problem part of your talk. So first question is, in the presence of Cheshire theta term and original axion term to the QCD, question is whether this can Cheshire theta term can destabilize the solution to the strong CP problem. In other words, I can rephrase this question into whether Cheshire term, when quarks are involved, which quarks talks to the gluon, whether can create extra potential to the axion, therefore shift to the Bevel,
Okay.
therefore display.
Good. We worried about this initially. The answer, very fortunately, is no.
Okay.
Because this Cheshire theta term, by the way that you construct it, you can prove that it cannot possibly affect the local physics of particles.
Okay.
So it only affects basically like how particles move around axion strings,
Okay.
and that's it.
I see.
So maybe that's too bad, actually, but that's how it goes.
No, it's good for you. Right. Although we know that axion Chern-Simons interaction, which is topological, we naively think that you naively think that it cannot affect the local dynamics, but QCD confinement changes the game completely, and in fact create a local potentials, and then actually affect
That's
it.
right. But there's that's right. But it turns out there's a very sharp difference between the standard Yang-Mills theta parameter and this theta parameter in such a way that it doesn't have this effect.
All right.
Yeah, I'm happy to tell you more later.
Okay, great. Thanks.
So usually whenever you have a theta term in d dimensions, you also have a quantized topological term in d-1 dimensions. So have you thought about what the implications of that would be?
The short answer is no. I very much sympathize with what you're saying, but I don't have anything intelligent to say. Yeah, it'd be interesting to try to come up with something, but we haven't so far.
Can I ask a second question?
Of course.
So this thing where you write, A equals theta times d phi. Well, I mean, no, like right at the beginning when you were defining the Cheshire theta term.
Oh, I see. Here?
Yeah. So I mean, is that just a kind of trick to generate a topological term, or is there some physical significance to what this equation means?
Yeah, sort of yes and no. So the way I've presented it, it's definitely just a trick to be able to quickly see that there's a 2 pi periodicity for theta. The part of the talk that I skipped, it turns out that this is how it always appears. You can prove, like on very general grounds. So it's actually both a trick and not. Initially, we came up with it as a complete trick, but then eventually it's actually the way it has to appear. So I don't know if that's helpful.